Am I audible? Yes. Yeah. So today I'll be talking about how we can use 21 centimeter signal as a probe for dark matter. And this is based on a work done in collaboration with Ranjan Laha. So let's get started. So first of all, by now we know that dark matter is there in the universe, but besides its gravitational nature, we actually don't know much about it. And that's why the mass range of interest is actually huge. So it starts from 10 to the minus 22 eV, goes all the way up to some solar masses. And as you can see here, that depending on the mass, there are different kinds of dark matter candidates. Now today we'll be focusing on this candidate, and the name of the candidate is primordial black hole, and the mass range of interest will be from 10 to the 15 grams to 10 to the 18 grams. So the first question is, what are primordial black holes? So as you have already heard, that primordial black holes are just like any other black hole, but the only difference is that these are formed at a very early stage of the universe. Now after formation, if we know the mass and the angular momentum of this black hole, we can determine their temperature, and that is given in the first expression, where this mpbh is the mass of the black hole, and this A star is the dimensionless spin parameter. And now depending on the temperature, what these guys will do is that they will Hawking evaporate. And what that means is that they will produce a bunch of standard particles, and the spectra for them is given here, where this gamma is called a gray body factor. That basically tells you what is the probability of a given particle to surpass the potential of the black hole. And finally, this E dash is the total energy of the emitted particles, taking into account the black hole's rotational velocity. So the next question is, how do you go about and search for these guys? So now the idea is, as I already said, that these are Hawking evaporating primordial black holes. So they are injecting new particles in the surrounding. So whenever we have a system that is injecting a bunch of particles in the surrounding, what will happen is that the temperature of the surrounding will go up. So if we have these Hawking evaporating primordial black holes in the early universe, what will happen is that the thermal and ionization history of the intergalactic medium will change. So right now what we need is that we need a kind of thermometer that will tell me the temperature of the gas at different redshifts. And if I see an anomalous rise in the temperature, I can say maybe this is because of primordial black hole. So this is the basic search strategy. And fortunately for us, there is a thermometer, and that thermometer is the global 21 centimeter signal. Now 21 centimeter line, as we all know, arises because of the hyperfine splitting in the ground state of neutral hydrogen. And for the case of the global signal, the idea is following. So when the CMB was formed, or the cosmic microwave background was formed, there were all sorts of photons inside it, and some of them were 21 centimeter photons. And the intensity of those photons are determined by the CMB temperature, and that is this TR. Now, while these photons are traversing the universe, they can encounter neutral hydrogen cloud, that is this H1 cloud. And inside this cloud, we have hydrogen atoms. They can have their own 21 centimeter transitions. And those transitions are actually governed by this quantity called spin temperature. So the whole picture is following. So from CMB, we have 21 centimeter photons traversing the universe. They encounter a cloud. Some of the photons get inside the cloud. Some photons get out of the cloud. What we measured in the experiment is the difference between the intensities of the photons that are going in and coming out. And that is precisely known as the differential brightness temperature. And this is the form of the differential brightness temperature. So from the left, we have the delta TB or T21, that is the differential brightness temperature. XH1 is the neutral hydrogen fraction at a redshift Z. Omega M is the matter energy density parameter today. Omega B is the baryonic energy density parameter today. This TR, as I said, is the background temperature, typically taken to be the CMB temperature. And last but not the least, we have the TS, that is the spin temperature. So at a given redshift, if you give me the values of all of these parameters on the right, I can determine the value of differential brightness temperature. And that is shown here. So in the y-axis, we have this parameter differential brightness temperature. In the x-axis, in the upper panel, we have the redshift. And as you can see by the black solid curve, that depending on the redshift, the nature of this curve is actually changing. Now you can notice that there are two troughs in this whole picture, and these two troughs are the thermometers for intergalactic medium. So what I mean by that is that if using some experiment, I can measure the precise values of this trough, then from that I can infer about the temperature of the intergalactic medium. So in other words, these are the thermometers that I was going for. So now that we have a thermometer, how do you go about and discovering primordial black holes? So again, the idea is very simple. So in the x-axis, again, I have the redshift. In the y-axis, we have the differential brightness temperature. And let's say this blue curve is something that you expect from your standard ΛCDM cosmology. You do your theory and you get this kind of trough. Now you build your own experiment and try to see the signal, and you measure this red curve as your signal. So now the problem that you're facing is that you are getting an excess over the standard expected trough. And what that tells you is that any sort of excess in this signal actually tells you that there is a possibility that during these redshifts, there is an exotic heat injection source. And one example of that is primordial black hole. So if in future we have an excess in the global signal, we can in principle try to search for these guys. Now, if your data agrees well with your kind of standard expectation, then also is very useful. because that actually enables us to put stringent bounds on the parameter space. And that is what we have done here. So the left plot is for the non-spinning primordial black hole, the right plot is for the spinning primordial black hole. So in the x-axis, we have the mass of the black hole in gram. In the y-axis, we have the FPBH. And this FPBH quantity tells you what is the fraction of dark matter made of primordial black hole. So if I say FPBH is 1, then all dark matter is primordial black hole. Now, the gray shaded region that you can see here, these are the combined limits that are put on by various astrophysical and cosmological observables. Now, I don't have time to go through all of them, but if you're interested, we can talk more about it. Now, here what we've done is that we have taken 3 different values of this global signal at redshift 17. So for example, let's look at this purple line. So what this says is that if at redshift 17, I measure my global signal to be minus 200 MK, then this purple line is my limit on primordial black hole dark matter. So anything above this purple line is ruled out. So as you can clearly see that just by taking into account the standard expected global signal, I can put very stringent limit on the parameter space. And that is precisely the reason why this global 21st century signal is such an important probe for new physics. Now, there is an experiment called EDGES, as you have already heard, and this is situated in the western part of Australia. And in 2018, it measured the signal for the first time. So in the x-axis, again, we have the redshift. In the y-axis, we have the brightness temperature. And this is the signal that they obtained. But the weird fact about this thing is that this is much deeper than expected from standard cosmology. So just to guide your eye, this red curve is something that you expect from cosmology, but what EDGES saw is much deeper. So the question is, how do you explain the EDGES signal? So here the basic idea is that if we just go back to the expression of differential brightness temperature, we have 2 quantities. This is the background temperature TR, and we have the gas temperature TM. So what you can do is that either you increase this TR and keep this TM fixed, that will decrease your delta TB, or you keep your TR fixed and decrease your TM or gas temperature, then also you have a decrease in the delta TB. So in either these 2 scenarios, you can explain this EDGES signal. Now, we have considered this kind of anomalous signal also. So for the left, this is the same plot. So in the x-axis with the mass, in the y-axis with the FPBH. The left plot, we have considered an excess background, and the right plot, we have considered a lower than expected gas temperature. And in these 2 scenarios, this red solid line is the bound. So again, the pink regions are all ruled out. So as you can see, these are complementary to the other limits that are there. But the main idea is that this depends on the assumption that there is an EDGES-like signal, and how do you go about explaining that result. So now there is an update on this EDGES. So as you have heard from Saurabh, that their experiment SARAS has not seen any excess suggested by EDGES. So maybe this EDGES anomaly is just a systematics. But besides that, there are other experiments like REACH paper, and all of these experiments are trying to look at this 21 symbol signal. So now all of this discussion, this EDGES experiment or SARAS, all of them are looking at this stuff at the beginning of reionization. So now you can look at this whole plot and wonder that is there someplace else where we should search for the signal? And the answer is yes. So there is this stuff from the times of dark ages. And what we actually argued in our work is that this will be a much cleaner probe for new physics. And the reason for that is very simple. We know for a fact that during the times of dark ages, there were no stars, there were no galaxies to affect the IgM. What that means is that let's say tomorrow I measured this signal from the times of dark ages and I see some sort of an excess, then there is no way that you can explain that excess using standard astrophysics. So in other words, any sort of excess from the dark ages stuff will directly point towards new physics. And that is precisely the reason why this is a much cleaner probe. And right now people are getting interested in actually exploring this stuff. So already there are some proposed experiments like DAP or far side, which will try to go to the far side of the moon and look at this high redshift signal. So in our work, what we did is that we took the standard expected dark ages stuff and tried to see what kind of bound we already obtained. So again, in the x-axis we have the mass, in the y-axis we have the FPBH, and this green and the red lines are our bounds. So again, the shaded regions are ruled out. So as you can see that these are competitive with the other limits. But the important thing to remember is that in order to discover new physics, we have to move to the dark ages stuff because there is no astrophysics to hamper our signal. So to conclude, we have seen that the global 21st signal can act as a calorimeter for exotic heat injection, and evaporating low mass primordial black holes can affect the gas temperature and affect the global signal. And in future, we hope that we'll have many more results from this global signal experiments. And by that, our understanding of the universe will improve, and also we'll know much more about the nature of dark matter. So thank you.